started. Let's see. This is a little messy. Let's see, I want the light on. Hello, guys. I hope many of you are joining. Retouch. Do I want retouch? Sure. Lighting on? Sure. Okay, let me go get some yogurt and I will be right with you. I hope that we will be chatting tonight, many of us, together like. So, let me get my yogurt. Also, I want to find my ring. I am here. Hello, dear. How are you? Put something in the chat. If you are joining, that would be most delightful. Hi, Logan. How are you doing? Hi, Logan. Thank you for joining. See your chat message. It is delightful to hear from you. Hello. I just found my rings. I kind of lost them. Didn't know where they were. And then thankfully, I now know where they are and I put them on for you guys. I have not been live in quite a while, guys. It's been quite sad how busy I've been. Should I put it up on this box like this so you can see more? And that does make it a very weird angle. Ooh, how about this? Does that work better? Hello, everybody. Give me 1 second. I will say hi to everybody. And if you want to shout out, then let me know as well. Where are you from? You should guess where I'm from. And also, could you like us? Could you give the live a like? Help out a small creator? Thank you. Where am I from? Well, I'm currently in Boston. Where are you from? I messed up the live, didn't I? Did I mess it up? It's okay. We'll just go like this with my chin in view. This view. This view is not the best view, but it will have to do. I'm gonna have some yogurt with you guys. How are you? Thank you for joining. Logan is saying you look beautiful. Thank you, Logan. Emily Knight. Emily the Knight is saying hi. Hello, Emily. Hello, Cloudflower. Hello, Fabian. Where are you from? I don't like guessing. You don't like guessing, but I love guessing. I had been told something. Hello, girl, dad, cooking up deliciousness. Hit that like button if you haven't. Thank you. I love guessing. I hate being told. I want to guess always. Is that Greek yogurt? Hi, an unknown derpy. Hello, burger. This is Greek yogurt. You're right. This is Greek yogurt from Target. It's called Chobani. Chobani Greek yogurt non-fat plain. 14 grams of protein, 0 grams of added sugar. No artificial flavors, sweeteners, preservatives, or gluten. I just get this from Target as a snack. I just came back from the gym and I like having these yogurts because they're a quick snack I can grab without having to cook something. Mm-hmm. 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 How are you guys doing? Please subscribe. Can everybody please like, share, subscribe? I really need the help. I really need it. Please like, love, share, and subscribe. And give us some hearts. I love when the hearts float up. Hello, unknown derpy. Burger is saying, I don't know why, but yogurt is so good even if I don't want it. Actually, yes. I am not a big fan, honestly, of the flavor of yogurt. I have got a sweet tooth. So, you know, there are certain yogurts, especially where I grew up, which somebody was asking, where the yogurt itself can, they prepare it in a way where it makes it very sweet. And so I like it sweet. But this is the healthy stuff that's not that sweet. But surprisingly, I kind of like Greek yogurt because it's got this like nice plain smooth taste, which I like. And it does make for a nice snack. I have a cut over here. Never me. I'm looking at my face. This is probably the longest I've looked at my own face because I'm on this phone camera and in quite a while because I've been so busy. It has been so busy indeed. And also my lights for the live are still partly broken. And so, yes, it's been a struggle, guys. I am appreciative that you all are here to support. Thank you so much. Fidel Torres. Oh my goodness. Hello, Fidel Torres. Torres is saying your personality is so attractive. Oh, thank you. Thank you, thank you. Also, my hair is in a lot of braids right now. Um, I went swimming. Baji. I'll let you know as soon as he's here. He might have gone upstairs. The kitty cats. Actually, I just opened one of the rooms where they like to play because I was getting my ring and my rings, both of these rings were kind of missing for a while there because I forgot where I put them. And that room is the guest room and they love to explore that room because usually it stays closed. So give us a moment. It might be a little while before we can see Abaji Baba here, okay? Thank you, Fidel Torres, again. Hello, K Roken builds. That and blueberries is a combo. Yeah, I don't have blueberries right now. I do have strawberries, and I ate some in the morning. I do like blueberries. Thank you for subscribing. I love strawberry yogurt due to acidity and sourness. Thank you, everybody, for supporting and liking and subscribing. I see number one is unknown. An unknown. I think that's Burger. Number two top fan is Girl Dad. Number three is Fabian. Number four is Logan. Number five is Fidel Torres. Thank you guys so much for being here. Okay, I also do have to share the live and things like that. So give me a second. Thank you for the likes. Hello, Derby. Derby's the Eternal. I like that. I love Eternal. What else is up, guys? How are you all doing? I haven't caught up with you in quite a while, so I want to ask how is everybody doing? Mm-hmm. I'm like kind of cold. Um, First of all, it is kind of cold still in Boston, Massachusetts, which is where we are. And also I went swimming, so I always get a little cold after swimming. I feel like I go live after my swims, and so people think that I constantly have a cold because I am actually kind of like sniffly and cold after I swim, but it's also my favorite routine to do. Uh, so for my wellness, and so here we are. Is there an ice walk in Antarctica? There are some marked sort of paths that you are supposed to stick to. So yeah, most of Antarctica is ice, and so pretty much you are walking on either ice or a bit of rock. There is some rock there from the volcanoes. Um, but not everywhere is safe to walk. So there are certain flagged paths, like there's little green flags that are put on the charted out uh, sort of paths that you should be following, and those are safe. And you're not supposed to venture away from those little green flags because then that is uncharted and there could be cracks or crevices that you could fall into forever and to your death. So um, that's that's pretty much it. But most of the time, you are walking on ice. Okay, so be careful if you're going there. You should do a hot or warm bath after swimming. I do. I actually, so today I didn't have time for the hot tub. The gym actually has a hot tub. I didn't have time for that because the gym is also like closing. So I did take a shower. I took a hot shower and then I got changed in the sauna. So I did do that. I did do that. That was nice. But make sure you dry yourself a bit before. Yes, it's true. Well, I dry myself in the sauna because I'm usually like showering and quickly getting dressed before I get kicked out of the gym because it's closing. Okay, let me share the live. I always forget. I just wanted to do a quick chat catch up with you guys because it has been a while since I did a live, and I read your comments, everybody. Thank you for watching my other videos and um all the shorts and content that come out. Shalom, hello Ben. How are you doing, Ben? It's been so long. I haven't gone live in forever. I missed everybody. So, yes, I was gonna say thank you everybody for watching my other videos, shorts and everything like that. I see your comments on them and I very much enjoyed that, so please do keep it coming. Um, Swimming is my favorite activity because while you're moving around the water, contrasts you, so it's a bit hard to move. Right, it's a kind of a resistance, right? Which makes your body adapt and makes you healthy. Oh, good. Well, I hope it's healthy because it's my favorite exercise at this time. It has been for a few years. I like to swim laps. I am very afraid of deep water, which is why I don't like the YMCA. Now, the YMCA near me, I actually have to check if the depth um, is something. Thank you, Ben, for the makeup brush. I have to check if the pool gets deeper on one end because I like a lap pool where it's not for diving. It stays the same-ish depth throughout because I'm very afraid of deep water. Although I can swim, and I do swim in the deeper water, like when I travel, like in the ocean and stuff. But um, I think there the trade-off is that you're usually doing a fun activity. But if I can help it, I don't like to go in the deep water. I like swimming for like 30 minutes or 1 hour, then I'm getting out. That's a nice amount of time. Thank you for the gifts, Ben. Bat, Batty. Uh, welcome to the chat. Thank you so much for the emojis. And thank you, Ben, for the gifts. Really appreciate it. Thank you, everybody. And also, thank you so much for your patience with my channel. I see your comments and kind remarks coming in. And that's always wonderful to read. And I will be adding more videos and shorts really soon here. So please do watch for that. And thank you so much for supporting as always. What is this? Oh, look at this. I now have games that I can stream with. Oh my God. Oh my God, guys. I didn't know about this. Um, there are more features on my live currently. Should we? Oh my God, there's a puzzle. A puzzle is starting. Should we do that? Have you any idea what this is? Oh my God, I'm able to play a puzzle. Okay, I have no idea. I think I can. Oh my God, I have never played a game in my entire life. This is my first one. This is my first one, guys. Honestly, I'm not much of a game person. I think I lost. It's letting me do it again. Oh God, oh God, oh God. I really don't. I really. Oh. To be honest, I really don't like losing. Um, 1 second, please. I need to. This is. All right. Guys, I have no idea what is going on. YouTube has given me an ability that I did not know I had, which is to play a game live with you guys. I punched somebody, or I got punched in the face, or now that I started this game, I cannot see your comments, so I will pull up the live on my other screen. Go on top of the handle. Okay. I'm gonna do it. Ladies and gents, I had no idea that this was an option, but it is. Apparently I can play a game while you're watching, as if there wasn't enough pressure already. But I love that you all are here. Where is the live monitor? Give me one moment, guys, because I can pull up the live on my other device here. Punch Ben. Oh my gosh. Please do like and subscribe, guys. I'm gonna pin that message. So I'm supposed to do the puzzle here. And this is my first time indeed that I have played such a game, to be honest. Mm. Where I'm from, there's no fun in games. I made a goal. Okay. All right. We're gonna redo this. I'm supposed to get that bag. Okay. Ah, 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 ah. No. There. Oh, oh, oh my God. Oh my God, I did it. I stole a bag. I did it. Oh my god, oh my god. Level 3, level 3. This is very difficult, guys. This is very difficult. What am I supposed to do now? Honestly, this was not what I had in mind. I thought we would be doing. That's the fire hydrant. Ah, ah, ah. There. Is this the groceries? Oh yeah, he wants the groceries. Oh my god, I'm helping people steal now. This is what things have come to, guys. Um, okay. I think I'm good at stealing, guys. Oh gosh. Okay. All right. Are you seeing this? Thank you, Ben. Did you guys know about this game? Like, wow. Thank you, Logan. Did you guys know about this game? All right. I'm gonna redo that one. Honestly, let me move my. It's kind of difficult with other things on the screen. Like, it's not letting me go over here. Oh, oh my god. This is America. Did I do it? I did it. What country is this? I'm in Boston, and never have I ever seen this before. Hi, Wild and Wavy. Wild and Wavy is saying I read a poem for you. It's titled Quantum Entanglement. Ah, well, what's the poem? Let us know. I cannot believe I played a game. All right. Okay, what do I have to do now? Oh, oh, there. Did I win? I think it just froze up. Hi, J. Hi, J Dub. Long time no see is correct. Hi. It froze. I see. So, I'm after the pearl. Okay. It's a little laggy. Maybe YouTube wanted me to try it out. But it's a little laggy. Do you see this? Are you guys hearing the sounds from the game? I lost that one. I'll redo it. I just had no idea that you could do this during a live. It's laggy though. It's laggy. Hmm. I tried. Oh my God. Wow. I just had to be sneaky. All right. That was the game, guys. I hope you liked it. That was my first time playing the game. Thank you, J-Dub. Thank you, J-Dub, for the butterfly. Oh my gosh. What happened with the other evil twin? I don't know. I don't know. I was just trying to survive. I was asked to steal things. 110. Thank you for the gifts. All right, guys. What should we talk about? This is Greek yogurt. Where is she? What do you mean? Who is where? Or who is she? Should I play another game? Thank you, boss. Nugget. These games are quite challenging on the little screen. I don't know if you guys play on something else. Okay, this is a puzzle. I don't know exactly what it will be, but it's a puzzle. We will play it. Oh, okay. Sorting puzzle. We get it. do something. All right. Okay. All right. All right. Is this what people do? I've never played such games. Is this normal? Is this what people do? Do you see this thing? It's kind of hard to get to. Like there's buttons on this side that I can't get to. But it's okay. We'll make room here. We'll make room. Oh. Alright guys, I feel like I could get kind of addicted to this, to be honest. To be totally honest. I found you, burger. I've never played games. This is my first time. In my entire life, I never played a game. Oh, how dare you. Oh, how dare you. Oh, please. Oh, do not joke with me. Do not joke with me. Be ridiculous. What is this nonsense? I see where you are. I see where you are. I see where you actually I really like puzzles, I think. I think I like puzzles. I can't get to the I cannot get to the right side of the screen here for me. I can't get to it. There are buttons there. Hee hee hee. Wait, what are these things on the bottom? Hi guys, thank you for joining. Please do like, share, and subscribe. Today we're doing a very different thing than usual, which is that we're playing a game. I cannot get to. Oh wait, maybe can I get it to? Can I get to it from my laptop, or is that cheating? It might be cheating. No, it doesn't let me anyway. I cannot get to it. I cannot get to the things on this side. Ben is talking about matter, antimatter. Oh, I love that. Hello. It is I. It is I. Hello, ice cream machine. I kind of wanted to do my puzzle, but it didn't work out very well. I kind of really wanted to do my puzzle. I like puzzles. Okay. Antimatter as a mirror. Antimatter is often called the evil twin of matter. Every particle has a counterpart with the same mass but opposite charge. When they meet, they annihilate each other. This is true, like electrons and positrons. Annihilate to make photons. What is that above me? That's a wall hanging cat tree. Wall climbing tree for kitty cats. Oh, my evil twin. My evil twin. Who is my twin? Did I make all the settings correctly? Did I do it? Stream. Oh. Oh, where is she, my evil twin? I see. I follow now. Logan, love you. Okay, hi. I'm gonna call this live fun and games. Hmm. I kind of liked that puzzle game. I think I'm gonna do another puzzle game and then be done. Shall we chat about particles and frequency? Oh, I love particles and frequency. I love physics chats. Let's do it. That's what we usually do. Maybe I just became my evil twin where I play games. Fun and games. Okay. Um, all right. We will now talk about let's do a some be evil and renegade. Let's do a little physics reading. How about that? Mm. Everyone has a doppelganger. You look very pretty. Oh, thank you. Let's do a little physics reading. Save that. Did I save? Did I share my live? I don't think I shared my live. Give me 1 second. Let me go get my phone and share the live. My other phone. Hello, Chris. Thank you, Logan. Thank you, Ice Cream. Hi, Ben. Environmental chemist. I want to read more from the physics person and discuss space and relativity. Well, you're in the right spot. We talk about physics, astrophysics, cosmology, astronomy, those types of topics on these lives, okay? Today we did a fun and games kind of live, but that's generally our topic. So right now the number one top fan is J Dub. Thank you, J Dub, for doing a gift. Number two is Ben Abraham. Number three is an unknown. Number four is Logan. Number five is Wild and Wavy. Number six is USA Guy. Number seven is Ice Cream. Number eight is Girl Dad. Number nine is Fabian. And number 10 is the Pink Batman. So if you want, are you funded by AI? I don't know what that is. Give me more details on that. Hello, Danielle. So, why don't we talk about a bit of space and relativity while we have our new friends here? Okay, thank you, Ben. While we have our new friends here, we can do a bit of space and relativity discussion. We came here for a reason, absolutely. Thank you so much, Ice Cream. I know you're smart, just looking at you and your physical being. Oh, thank you. Let me get my other phone and share the live, and then we'll talk about some space and relativity situations, okay? So, in fact, I can probably tell you about gamma ray bursts today. Ben, do you like gamma ray bursts? Uh, I know you talked about the what do you call the annihilation between particles, as in particle and antiparticle. So that made me think of electrons and positrons annihilating to make a photon. And of course, depending on the energy, electron and positron can annihilate to make a gamma ray. And so then that reminded me about gamma ray bursts, which is part of my thesis. So we could talk about that. Do you think Artemis really traveled around the moon? That's the plan for the mission, isn't it? I don't know exactly where they are right now, but they launched and they are going to the far side of the moon. So I would assume that that's what they're doing. I think that was the whole point of their mission, but we can also look it up. Yes. We can look up where these people are just now. But yes, 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 yes. Okay, we have started a live. We are live. Protons, neutrons, and electrons. Anyway, do we believe aliens been? I think they're just going to our regular old moon, just visiting. Yes. We could talk about the moon, by the way. The moon's surface has some similarities with Earth, but it's also very different. It's more simple. Um, and the moon does not have a lot of activity, as in no volcanoes on the moon. So that's why we still have craters on the moon, because volcanoes did not erupt and pave over those ancient craters from the various impacts that the moon had. Um, things cratering the moon with their impacts from planetesimals colliding and bombarding different surfaces of this solar system. And because the moon doesn't have other activities going on like volcanoes and things, a lot of that old stuff is still there, and the surface is um, cratered and older than most of the Earth's surface. So in that sense, the moon is quite different, but it's also similar in other ways. We are live, and we even played a game or two. Can you believe that? What kind of live we're having that we also played a game on the live. So, any other questions, or should we just get into it? Iona Mead. Oh, that's nice. You have a telescope, an autostar, and I've seen things very strange with it. Oh, thank you. Thank you for kind comments. Thank you. So, why don't I tell you guys about gamma ray bursts from my thesis? And that will be a little physics part of the live, okay? And we already did some relaxation with the game. And sometimes we talk about physics and then we go on to talk about um, something chill and relaxing. But today we already did the chill part. So, uh, okay. So now my thesis, I bookmarked it so that I can share it easily. So where is my bookmark? Ah, there it is. So if you wanted to read my thesis, which is in particle astrophysics, the isotope helium-3 is also heavily targeted for future mining due to its abundance on the moon. Ah, we need that fission element. Okay. I see. I didn't know about that. But well, if you're interested in particle astrophysics, which is of course a mix of both particle physics and astrophysics, and pretty much astrophysics done with the particles other than visible light, then I'm about to share my thesis, okay? I have many questions. I do not believe there are people in this ship. Oh, why not? There are people that are on this mission that are doing that right now. Um, I understand some people may have their doubts, but I do believe that that is happening because I think it's quite doable. Okay, so all right, so now let's talk about um so that's my thesis that I just shared in the comments there. Um hmm, in the chat, it links to a public document. It's been published and it is free and completely available to the public, along with other people's, there's everybody's thesis should be public. So it is there if you want to take a look. Now, we are actually going to be referencing it during this particular discussion of gamma ray bursts because I have it already here. Just have to pull it. This is like watching Jeopardy. What do you mean? Is that another game that I know not of? Not very familiar with fun things like games and shows. This is very tight. Um, okay. All right. So, mm, so since you guys mentioned space, relativity, particles, and such, we can real quick talk about something that kind of touches upon all of that, which also happens to be my favorite kind of transient. So this is chapter 5 of my thesis. TV game show about trivia. Hello, Javier. Oh my goodness, I'm here. Sorry I was missing. Thank you guys so much for being here. I really appreciate you. Interesting ice cream. This is like watching Jeopardy TV game show about trivia. Hello, I am Dude. Hello, Javier. How are you doing? Is the live still working? Hello, my dear friend. Sorry I've been so missing. Thank you for the emojis. So, to go to bed, um, knowing something new, we will talk about gamma ray bursts in this moment. Um, from my thesis. So it's nothing too new, but hopefully you get some value out of it. Why are they using fuel rockets when they have levitation? Levitation? They need to escape the gravitation of the Earth. So they need to do quite a bit of work to escape the gravitation of the Earth. Okay? So that's why they need fuel in their rockets. Does that make sense? Honestly, I understand your struggles with this moon mission because I have my own struggles opening this sparkling water bottle. Gravity is only a theory? Well, we do experience, I mean, there is some, there's quite a bit of practical evidence of gravitation. Now, as far as which theory you want to use, which one is more accurate, that could be debated. So I mean, not debated, but considered. So Newtonian gravitation is the older way of looking at gravitation, and the newer way would be general relativity. But there is a lot of evidence and practical, um, what do you call, proof and experimentation of these things. So gravity is not just a theory. It is experienced practically. Okay, and to escape that gravitation, so to not fall back on the Earth immediately. Um, I mean, even the moon is falling towards the Earth, but in a way that makes it orbit the Earth. It follows the geodesic. So in terms of general relativity, it follows a straight line path in four-dimensional space-time, that makes it basically appear in that orbit around us. So even the rocket will, you know, eventually eventually fall back to the Earth, but it needs to be accelerated um, to go do its thing first. So that's why there is the rocket and the fuel and whatnot. Okay. Hmm. Thank you so much for liking the live, by the way. Could we get 20 likes? The anti-universe recent. Hi, Snuggle Boy. How are you doing? I missed you. Can we get 30 likes? Okay, so let us now talk about gamma ray bursts, which may or may not be a transient event that you have heard of already. If you have, then good, because then this will be kind of like a review to you. And if you have not, then I am happy to oblige and tell you about it right now from my thesis. More anti-gravity ships. Hello. We need more advice technology. I've missed you too. Thank you. Hello, listen. I am goated. How are you doing? How are you doing? Thank you guys, everybody. It's so nice to see everyone after such a long time. We need more advice technology. What do you mean by that? Advice technology? I know not what that means. Welcome all. Okay, so now let me just read for a little bit so that, and then I'll catch up with all your comments, okay? So, gamma ray bursts are some of the most are, well, the most actually, not some of the most. I was gonna say something else, but I have changed my mind. Gamma ray bursts are the most luminous transient events in the observed universe. So these are things that are incredibly luminous. We will get into some of the numbers to describe the luminosities of gamma ray bursts really soon here, especially in comparison to other events in the sky. Um, but even though these are pretty brief events, so it's not like a gamma ray burst is happening, for a very long time. As you know, we'll get into the lengths of the event as well in time. But and also we will get into the parts of the emission that that we are kind of talking about here as well. But for example, a supernova, which is the death of a star. Thank you for liking the stream. Thank you, everybody. Can we get 30 likes? So a supernova is the death of a star, and this event you can actually see if you happen to be in view, you can see this event happening and emitting light for quite a while. Now, gamma ray bursts are different. They are some really extreme transient events, and so they will not be as long as the supernovae typically. Okay, so we'll get into some of these details. So even though they are not the longest of such explosive events, but they are the most luminous. So I'm a physicist. My background is in physics and physics. And the subfield I'm in is particle astrophysics. So this is why I know of these things. Okay. So when a gamma ray burst, are you real? Yes. hmm Thank you, listen. Thank you so much. So when a gamma ray burst is occurring, because it is a transit event, they can outshine an entire galaxy. Gamma ray luminosities of gamma ray bursts. So basically, gamma ray bursts are called such because they are emitting gamma rays, some of the most energetic photons there can be. Okay, so because photons are just light particles and they can have different energies depending on their frequency and or their actually their wavelength or frequency. Either way, basically, the more frequency the photon has, the more energy it has, and some of the most energetic photons are gamma rays. Okay, so a gamma ray burst is putting out a bunch of the most energetic photons or gamma rays, and now we're talking specifically about those gamma rays because other things may also be emitted from gamma ray bursts, and gamma ray luminosities are of the order of 10 to the 52 ergs per second. So now this is um, a unit of power, basically energy per second. So something like, excuse me, something like ergs would be an energy unit. It's not the SI unit for energy because, as you might know, SI unit for energy is joules. Ergs is another unit, and you can look up exactly how it relates to like joules, for example. But in astronomy, often used is this ergs per second. Now, once we do energy unit per second, it becomes like a power. Okay, so this is how a lot of the luminosities are expressed like a power. Okay, so gamma ray luminosities, um so just those energetic photons coming out of the gamma rays can be of the order of 10 to the 52 ergs per second. So even for example, another thing I wanted to bring your attention to, say for example, everybody deals with a power bill, right? Electricity, your bill. um Oftentimes that is reported as watts, or more um, commonly kilowatts. So your electricity bill probably has kilowatt hours on it. So what they're doing is actually, kilowatt is the power unit, and then they're uh, multiplying by the hours to basically give you your energy usage. So hopefully that's making sense. Something like this is the case with gamma ray bursts as well, but we can express it in terms of energy, or we can express it in terms of power. In this case, we're expressing in terms of power, which is energy per uh, second, okay, or energy per time. So anyways, this 10 to the 52 ergs per second is a very big number because you can compare it to, for example, 10 to the 33 ergs per second, which is emitted by our sun. So our entire sun uh, is emitting 10 to the 33 ergs per second. And this transient event, gamma ray burst, is emitting something like 10 to the 52 ergs per second. So quite a bit more. And then you can also compare the 10 to the 52 ergs per second to what is emitted by a supernova, something I was mentioning earlier. Supernova is the event that happens when a star dies, and that is going to be 10 to the 41 ergs per second. Or you can also compare it to the whole galaxy, uh, an entire galaxy, which is going to be 10 to the 45 ergs per second. So you can see how these numbers being represented in power units, it makes sense, right? So instead of the entire energy, if we do it in power, then we can kind of compare and get the luminosities out like that. So now you know that gamma ray bursts are the most luminous events because of their very, very high luminosity number, which is 10 to the 52 ergs per second, as compared to an entire galaxy would be 10 to the 45 ergs per second. Okay, so a little bit of history. So that was just to kind of put it in perspective. Um, how very luminous, um, how much, really, how much power is coming from these events. Um, Yay, you love astrophysics. Okay, good. This ring is actually a sponsored ring. We have talked about this before. It is a brand of ring that you can get yourself. So, Mother's Day is coming, and if not for your wives, you should be getting this ring for your moms. And I will find the link for you. So, don't you worry. Ben, do you have the link? Can you share it if you do? Because I'm busy right now. Um, uh, so this ring is not from a partner, but from a brand, okay? Um, I will get you the link. So now let me keep going. A bit of history on how gamma ray bursts were discovered for the first time. Hello, Frederick. I want you to consider the ring, not me. You should buy this ring for your mothers, for Mother's Day. That's what the ring company told me to tell you. Okay? All right. First discovered in 1967. So, this may actually kind of resonate with some of you here because pretty much in those times there was the Cold War going on between the U.S. and Russia, and there were a lot of efforts to basically spy on each other, and okay, and pretty much some defense people were kind of looking for different signatures and signals and things like that to kind of stay aware of what types of inventions were happening and what kinds of weapons might be getting developed by enemy countries. um, and lo and behold, they ended up discovering this very you know interesting event, and at first puzzling event, and to an extent there are mysteries still about gamma ray bursts, and so it's not all solved or all known even now, even though of course it's been quite a long time since 1967 at this point. But anyways, they were first discovered in 1967 by the Vela satellites flown by the US Department of Defense. um, Even though it's been a very long time, I believe almost 60 years, if I'm making that estimate correctly. uh, Gamma ray bursts actually still continue to puzzle scientists even today, because, like I was saying, there are still certain things that we don't know about gamma ray bursts. However, research in the past decades have revealed much about them, including that they are extragalactic in nature. So these are the things that we do know. So these things are extragalactic, isotropically distributed. So in the sky, they seem to be there isn't sort of a direction associated with them. Like, it's not like we get more gamma ray bursts from this direction versus that direction. Pretty isotropic in distribution as far as where in the sky, which direction they're coming from. Because we do have a list of gamma ray bursts that we see every year. And pretty much when you then plot that list, in get the geometry of where these, gamma ray bursts seem to be coming from, you will see that they are pretty isotropic. And also we do think that they're extragalactic. We don't think that there are gamma ray burst sources in our own galaxy. Um, mm, that's your specialty? Okay. Oh my gosh, Ben has some interesting insights into this. Okay, let's keep going. So, the other thing we know about gamma ray bursts is that they come in two populations, short and long. So, we kept it simple in categorizing them. These are either short gamma ray bursts or long gamma ray bursts. Okay, so gamma ray bursts are classified as long if they are more than 2 seconds long. So, these things can be typically quite short. Typical um, length is around 2 seconds. So if they're longer than 2 seconds, they're called long bursts or long gamma ray bursts. If they're shorter than 2 seconds, they're called short gamma ray bursts. Now, since the writing of this thesis, we actually have some new and exciting insights into gamma ray bursts. But at that time, long bursts we knew were associated with the collapse of massive stars or hypernovae. So basically, the long gamma ray bursts are like supernovae, but super duper supernovae. So they're called hypernovae. So a more extreme case of the cataclysmic explosion from a star dying. A hypernova is pretty much associated with the long gamma ray burst. Short gamma ray burst is going to be associated with mergers of binaries composed of neutron star, or neutron star black hole. Now, this part was actually theorized, but we didn't know for sure. There was no evidence until we got gravitational waves detected for the first time with LIGO. And that only happened in the last several years. It's been a few years now, quite a few years, but this was actually proven for the first time when we detected gravitational waves for the first time with LIGO. And so it was very exciting that we started to literally, confirm some more things like the origin of the short gamma ray bursts. And we truly started to do multi-messenger astronomy when we start to see things in this way. So, for example, gamma ray bursts will emit gamma rays, right? If you're also getting gravitational waves, then that's another way of probing the event. If you're also getting maybe, say, other types of particles like cosmic rays or neutrinos, then that's another way. And so, really, this is getting into multi-messenger astronomy, which is, of course, sort of that's another way of looking at all of this. And I talk about multi-messenger astronomy also in my thesis just earlier on. It's sort of in the introduction. Okay, so yeah, this was really huge when we realized that um we had kind of known for a while that the long gamma ray bursts were um associated with the hypernovae, but we didn't fully confirm that the short gamma ray bursts were associated with the neutron star, or black hole mergers. And now that is confirmed. In August of 2017, for the first time in history, so I talk about this, I think I had to add this in, I defended this in 2018. But so yeah, I guess by the time I defended this thesis, it was actually confirmed. We had started to see the very first gravitational waves getting measured when I was working on this. So, or when I was getting close to graduating, that was the time that we first, for the very first time, started to measure gravitational waves directly. Okay, so it was a big deal. Can a wormhole exist, or does it collapse immediately? We can talk about wormholes. um, you know, Einstein Rosen bridge. We can talk about that topic, but honestly, I don't know if wormholes really exist or not. Is there an audio sync delay? Can you guys hear me? Are you suggesting we're on a flat plane? Like a flat earth? The earth is definitely round. Um, are you guys having problems with the audio? Really? Can you not hear me? Well, that sucks. Oh no, that's never fun. When the audio doesn't sync with the mouth moving, that's not fun at all. Wave function collapse and the whole new philosophical idea that observing nature creates reality. I hope we can touch that. We can definitely talk about quantum mechanics probably another time. We have talked about quantum mechanics and its many quirks, uh pun not intended, quite a bit. Okay, so we can definitely do that. Cannot sleep with the yeah, it's been a terrible time over there. In August of 2017, for the first time in history, multi-messenger observation of a short gamma ray burst was performed by the LIGO, Virgo, and Fermi collaborations. So Fermi is the gamma ray observer. So you might have heard of the Fermi gamma ray burst monitor, for example. Um, so anyways, so LIGO, Virgo, and Fermi together confirmed the association of short gamma ray bursts with the binary neutron star merger. Okay, so this is very important because this happened for the first time in history while I was in grad school, actually. And there. This is very important because this was the first time that we directly measured gravitational waves. Um, and because we were also looking at also getting the gamma rays from a short gamma ray burst event, we now confirmed that association of short gamma ray bursts with the binary neutron star merger. This marked the first observation of a messenger other than photons from a gamma ray burst. So now we'll get into this later, but there are other theoretical predictions of other types of particles from gamma ray bursts, such as neutrinos. But so far, until 2017, the only particle that we had seen from gamma ray bursts is the photon, like extremely energetic photons, for example. uh, we hadn't really seen another signature, and now we did with the gravitational waves. So this was a game changer. And truly, like I said, we were starting to go towards multi-messenger astronomy because if you can learn about a single type of event or source with more messengers than just one, then it's called multi-messenger astronomy. So photons plus now gravitational waves and maybe even other particles going forward. So, first observation of a messenger other than photons from a gamma ray burst happened that time in 2017. So, I guess it's been almost 10 years. Indeed, no other messengers or particles have been known to come from gamma ray bursts, although theories predict that gamma ray bursts are environments where particles could get accelerated to the highest energies. So now we're getting into some other particles potentially as well. And there are certain theories about gamma ray bursts. Now, because this particular site, a gamma ray burst, would be something that would be very far away, it can be tough to know exactly what is happening in such an event. Okay. So there are certain predictions, like I was saying, from gamma ray bursts, and certain processes that are predicted for gamma ray bursts, which basically involve, accelerating particles in a very extreme way. Basically, these are nature's particle accelerators. And such processes are predicted to produce something like even neutrinos. And so, if we detected neutrinos, for example, from a source like a gamma ray burst, that would be confirmation of those types of processes. So, so this was the point. Actually, this one of the goals in the thesis was to kind of design a search that can look for these types of neutrinos from sources like a gamma ray burst. So, the detection of gamma ray burst neutrinos, so neutrinos that are um, coming from gamma ray bursts. So they are not just neutrinos from anywhere, but they would have to be confirmed, like associated with gamma ray bursts. And if we did that, then that would provide an unambiguous proof for hadronic acceleration in these cosmic explosions and could also explain the origin of the cosmic ray flux at ultra high energies. So there is a process called hadronic acceleration where basically hadrons are also getting accelerated in a big way in gamma ray bursts. Now we already know about um, you know, other leptonic acceleration, which leads to the gamma rays. But pretty much, if we don't have the hadronic acceleration, then we probably would not be getting the neutrinos. So if you're predicting neutrinos from gamma ray bursts, you basically have to go through that hadronic acceleration process. So pretty much that is to say that we are kind of trying to understand what goes on inside a gamma ray burst beyond just understanding about the gamma rays that come out of gamma ray bursts. Okay. So beyond the leptonic acceleration, there could be other processes too, which would predict neutrinos. So because I was on a neutrino experiment and we were trying to um, discover neutrinos of these very high energies, ultra high energies, one of them, I would say maybe one of the most, and to me at that time, it was the most important question, was to see if such astrophysical neutrinos could come from a source like a gamma ray burst. So the detection of gamma ray burst neutrinos would provide unambiguous proof for hadronic acceleration in these cosmic explosions and could also explain the origin of the cosmic ray flux at ultra high energies because cosmic rays could also come from gamma ray bursts. From gamma ray observations alone, theorists have hypothesized that regardless of the nature of the underlying source or progenitor, so whether whether the source is a hypernova like a dying star or a merger between two neutron stars or neutron star black hole, pretty much we expect um, gamma ray bursts to be coming from a dissipation of the kinetic energy of a relativistically expanding fireball. So there is some expansion going on, and not just expansion, it is a relativistic expansion. It's a very extreme kind of environment. Okay. Um, Protons may be Fermi accelerated in this dissipation region to energies of more than 10 to the 20 eV. another another unit of energy. Interactions between gamma ray, fireball gamma ray photons of energy about 1 MeV and accelerated protons of energy of around 10 to the 15 eV could lead to photomeson production. So basically, if protons, for example, in this environment were to interact with photons in this environment, they could lead to these what we call the photomeson production of pions, another type of particle, which would, it's an intermediate particle, so it would decay. Upon decaying, it would result in an accompanying burst of neutrinos of around 10 to the 14 eV. Now, this is all in papers by the way, I believe this person is actually from your same country, Ben. You should, so Eli Waxman is the person who has a number. I'm going to put that in the chat as well. Um, you might know him. Ben, do you know Eli? I didn't quite give you the. Let me go to the actual source. Give me 1 second. So actually, a lot of the gamma ray burst theory papers that we are talking about here um, is by one of these guys, actually, Eli Waxman. Um, and so that's one of the sources. Well, that's one of the papers. Gamma ray bursts, the underlying model. Um, okay. And there are more. there are many more, and these are all cited in my thesis as well. But basically, now I'm gonna go back to the where I was. This is chapter 5 from the thesis that I linked earlier. So Waxman, Buckle, a couple of guys actually wrote a number of papers on this process that could pretty much produce, like it gives us a way it gives uh, provides a way for neutrinos to be coming out of um, gamma ray bursts. I believe the Eli is Eli. Let me Google him really quickly. I think he is my connection on LinkedIn. Yes, Eli Waxman. Maybe I'm saying it wrong, but he is at the Weizmann Institute of Science. Isn't that? Do you know the Weizmann Institute of Science, Ben? That's where this author is from. And him and John, I think John Beckall, I forget the first name. Pretty sure. Yeah, John Beckall. The two of them wrote many of these papers. Yes. See? So John Beckall, who is from the US, and this Waxman from Weizmann Institute of Science, the two of them wrote a number. Eli, yes. Is that not how you say it? Is it Ellie or Eli? I thought it's Eli. Eli Waxman? Okay, anyways, so these two people, they wrote very many of these papers. Okay, so once again, this process, which would require hadronic acceleration within these sites, sorry, I got distracted. These this process, which would require hadronic acceleration in these cosmic explosions, um, pretty much that thing I said, the interaction between, for example, a proton inside a gamma ray burst and a photon. And of course, there are some estimates for the energies of each of those things, would then lead to some intermediate particle, photomeson production of pions, which upon decaying could result in an accompanying burst of high energy neutrinos. Now remember that I was working on an experiment that looks for ultra high energy neutrinos. Now there are also high energy neutrinos that have been measured already by other experiments. More and more have been measured over time, but ultra high energy neutrinos too were being looked for. And pretty much the more explanations or predictions of such types of neutrinos, the more motivation one would have to look for them. And gamma ray bursts, clearly having this kind of theory and sort of prediction for a burst of neutrinos was a huge motivation for me to look for neutrinos from such transient events. Okay, so that's why I looked into gamma ray bursts and looked into like understanding them better and things like that. So that's what's going on. But I did want to mention that Waxman and Bocall are the two people who have written a number of these papers, and they're not new either. Like for a while now, they have been trying to, get the predictions down, more narrowed for what they exactly expect from gamma ray bursts in terms of the neutrinos, what energy of the neutrinos and how much of the neutrinos, the flux. But I will say that, of course, the theory papers, they can do a good job of estimating and things like that, but we would of course rely on experiments to actually measure and make measurements. And remember, if you cannot find a neutrino, you end up basically ruling out neutrinos from a particular source or process. Then you're putting a constraint on the theory that predicts that flux of neutrinos. So let's say the theories predict some flux versus energy of neutrinos, and you end up seeing something different, or basically if you don't end up seeing any, then you would pretty much constrain the curve down and say that whatever the theory predicted or expected us to see, we're seeing a lot less, so this curve has to look different. So even basically not finding something is still a result in this type of work, in especially this is particle astrophysics. So that is actually quite common. So, but yeah, I talked about cosmogenic neutrinos at one point here, remember, because, basically that type of neutrino is something that is interacting with maybe a CMB photon. So it's not very different in the particle physics process of it. Like, there's also cosmic microwave background photons, and pretty much if a particle like a proton comes into contact with a CMB photon, um, not as exciting of a photon in that sense, but still a photon, then it could also go through those types of particle interactions that end up leading to neutrinos. So that would be sort of a more what we call cosmogenic way of getting um, neutrinos. And the astrophysical way of getting neutrinos would be something like this, which is what I found to be more motivating, which was my basically what I really wanted to go after. Okay. So this is why I am ending up giving a sort of introduction to gamma ray bursts, because this would have been the astrophysical source later on that I would take a look at as far as the neutrinos. So let's keep going. Okay. So it is important to understand gamma ray bursts, because ultimately here what we're doing is both astrophysics and particle physics, and we're basically trying to probe astrophysics with particles other than visible light, in this case neutrinos, but of course it can be other particles depending on the experiment. So some people, like I mentioned with LIGO Virgo, they look at gravitational waves measured directly from various events. Some people look at cosmic rays like Auger, and then my experiment looked at neutrinos. So anyway, coming back to gamma ray bursts, because they're an exciting event in astronomy, and I like astronomy. So gamma ray bursts are characterized by a two-part emission. So this two-part emission is basically the prompt emission and then afterglow. So I mentioned earlier that a typical gamma ray burst is about 2 seconds long. Short gamma ray bursts are, you know, shorter than 2 seconds, and long gamma ray bursts are longer than 2 seconds. So sounds like a pretty, broad way of categorizing them. But um, within the emission and what is kind of going on with the emission, you can further try to understand sort of the science, and also it kind of informs the observation of gamma ray bursts by looking at this prompt versus afterglow. So prompt is going to be like the prompt one. Um, and afterglow is a much longer period of time. And now I actually spoke with, so this is where some of the experimental details come into play. So I'll go into the prompt and afterglow definitions here in just a second, but I wanted to mention that I spoke directly with the gamma ray burst, some of the, um, premier gamma ray burst experimentalists, like observers, people who observe gamma ray bursts, and they actually said that sometimes the afterglow of a gamma ray burst is how long it is because of observation, because they simply gave up on that gamma ray burst and they didn't want to keep observing it any longer. So this was also something that was important for me to understand, actually, because you will see how this can affect neutrino observation from gamma ray bursts. So this is to say that, sometimes when science results are published, there is usually a deeper layer to go into. If something says that an afterglow was a week long, you might want to ask, if is it a week long because it was truly a week long, or because the telescope needed to look somewhere else after a week and we couldn't follow it any longer and nothing interesting was happening, uh, you know, uh, interesting to the person pointing the telescope was happening beyond a week. But of course, what is interesting to a person can also vary from person to person. So, for example, I was interested in finding neutrinos from these types of sources, and that is going to be very different than some of the other types of particles. So, as much as you know, we are definitely in a mode of doing multi-messenger astronomy in today's day and age, but also remember that historically, people looked with light, and the signature of light is going to be very different than the signature of neutrinos. Okay, and how long you might have to look if you're looking for light versus neutrinos could also be different, and we'll get into more details of that in a bit. But just wanted to mention that how you look, how long you look, where you look. Well, hopefully, where is the same direction you would look at, but um, of course, the methodology of the technology of what you look with, etc., all vary a lot depending on if you're looking for light or neutrinos or cosmic rays or gravitational waves. Okay, so gamma rays are emitted during the prompt emission period of the gamma ray burst. So gamma rays are the most energetic photons, and because photons can have other frequencies, other energies as well. You could have a photon that is X-ray frequency. You could have a photon that is a radio wave frequency. You could have a photon that is ultraviolet UV ray frequency. Um, the UV rays that we wear the sunscreen for. Or you could have photon that is a gamma ray frequency. That is the shortest frequency, or sorry, the highest frequency and the shortest wavelength. So, so depending on the type of light or the type of photon and its frequency, you will get the different kind of photon and different kind of photon energy. Photon energy goes as um, Planck's constant times frequency. So more the frequency, more energetic the photon. So gamma ray bursts have, or sorry, gamma rays have gamma ray bursts. Prompt emission will emit gamma rays or photons of gamma ray wavelength and frequency, and that frequency is very high, so that energy is also very high. Okay, so the some of the highest energy photons will come out during the prompt emission of a gamma ray burst event, followed by softer and softer photons. What do I mean by softer and softer photons? So less and less energy photons. So softer photons versus harder photons. Harder photons are the more energetic photons. Softer photons are the less energetic photons. Okay. So gamma rays are emitted during the prompt emission period, followed by softer and softer photons, such as X-rays, UV rays, and so on during the afterglow emission period. So pretty much that prompt emission has the gamma rays. So as long as you get your gamma rays with your gamma ray detector, then we call that the prompt emission phase of the gamma ray burst. But then as you start to get the softer and softer photons, like now you're getting X-rays, UV rays, that can be, or even radio waves, that is the afterglow emission period of the gamma ray burst. So it's important to understand this prompt versus afterglow emission period, and also remember that prompt versus afterglow will also mean that there is potentially different physics going on at the site, and what else you can expect depends on that physics. Okay, so um, neutrinos are predicted from gamma ray bursts following an opposite spectrum to that of photons. So this is an insight that I thought very deeply about in grad school, which is that actually um, neutrinos are expected with the opposite trend. So, in other words, harder and harder energy neutrinos with time. So, it turns out that the softer the photons get, you would actually get more energetic neutrinos. So, if we're saying that the highest energy photons come out in the prompt emission, well, then actually in the afterglow emission, you could expect in that logic, you could expect the highest energy neutrinos. And so the fact that maybe people stopped looking at gamma ray bursts after a certain period of time because they're not interested in the afterglow could actually be kind of going against um, trying to find the neutrinos of higher energies. So I have a little diagram here that I can show you in a moment, but that basically shows you that the neutrinos follow the opposite trend as photons. And so when you start to get the lower energy photons is when you would start to get the higher energy neutrinos, because the photons and the neutrinos are coming from different processes that are sort of complementary. So and also, of course, the fact that you would get neutrinos at all depends on whether you had a certain type of Fermi acceleration in the gamma ray burst, which affects the hadrons in the gamma ray burst. That is not confirmed until we get neutrinos from gamma ray bursts. So that is still a theory. Okay. But of course, the what do you call it? The leptonic uh, acceleration is not a theory because, of course, we see gamma rays from a gamma ray burst. Right, so where is my flow chart? I thought I had a flow chart that can explain this. I will find it and show you that as well in a moment here with some explanations, because that one, oh, here it is. Yeah, so I'll show you this flow chart in a moment. That will help. Okay, we'll keep going. So gamma ray bursts are actually extremely diverse. So, which makes sense, right? When you have something like the typical is 2 seconds, but the uh, short ones can be less than 2 seconds, the long ones are more than 2 seconds. Well, guess what? Some long ones are really long. So there is a lot of diversity. The prompt emission is typically between zero point 0.2 and 20 seconds long. So there's quite a bit of variation there. So anything between 0.2 seconds and 20 seconds is quite a bit, variation. Note that the prompt emission can occasionally last for several hundreds of seconds, as was seen in the case of the 5,400 second long gamma ray burst that was reported. I have the paper in my thesis, but basically there was a while ago there was a 5,400 second long gamma ray burst. So that tells you that there is a great uh, variety of them. There is a great diversity of these things. They're not all the same, right? And that kind of makes sense because not all of these hypernovae, I mean, they're all different stars that are dying for the long gamma ray bursts, and they're all different short um, gamma ray bursts as well. But like, depending on the case of the neutron star merger or the neutron star black hole merger, you could see how the phenomenon underlying the gamma ray burst could be very different from each other. The exact parameters involved, like the masses of the objects that are colliding in the case of the merger, or the mass of the star that is hypernovaing. Although I would imagine that um, it would be a very massive star that uh, you know that would hypernova in order for there to be a long gamma ray burst. So, well, so but I guess even there is some variation. So, the afterglow emission time period for gamma ray bursts is even more diverse, and this is where it gets a little tricky Because, like I was saying, sometimes, can we get 30 likes, by the way? Sometimes the afterglow period is as long as it is because they simply stopped observing. They just, ran out. They're like, we have to point the telescope somewhere else. We can't give this object any more time because we have limited resources and we can't spend forever on the same thing. So, the afterglows can actually last from anywhere between, so the afterglow period of a gamma ray burst, right? Which is actually going to be very important to us. So, the afterglows can last from anywhere between few minutes to several months. Swift scientist at the Mullard Space Science Laboratory. So this is in the UK where I visited. Matt Page, there was this person working there, showed me the flux versus time plot of a gamma ray burst with afterglow observations in X-ray that continued for over a year. So this is how much variation there can be in afterglow. Matt shared that eventually the observers decided to move on and assign observation time to other objects. Afterglow records might not be available for a few other reasons. So this is what I mean. There can be some gaps in the afterglow records because they might simply have to move on from that source and go look at something else because that takes more priority. So it is going to be tough to understand, you know, all that goes on. Sometimes just because time is an issue. Sometimes afterglows are not observed at all, as no telescope is pointing at the object for follow-up in afterglow because they consider the gamma ray burst, where the gamma rays are being emitted, as sort of the main signature. So they might simply not observe anything in the afterglow because they're like, okay, we're done. They don't have a motivation necessarily to keep looking for the afterglow. So that can happen. So the absence of a record for an afterglow does not necessarily mean that there was no afterglow. Moreover, afterglow photons can get absorbed by dust and not be able to reach us, thanks to my discussions with Swift observers at Mullard Space Science Laboratory for these insights. So so basically, if one is looking for neutrinos from a source like a gamma ray burst, I would design the search in a way that constrains in direction to regard for the, to account for the gamma ray burst, but maybe not constrain in time, because typically in time constrained searches for neutrinos, there are actually like basically intervals of time that people pick, and they do the search, and they, basically there's a lot of mechanics of the search itself that would be um, affected by this. How you design your search, what you use for the search versus the um, setting thresholds and the blind analysis, all this stuff can be affected. So pretty much constraining in direction was something that was not done a lot when I was working on all this, and that's what I suggested, is that you actually have to constrain in direction and maybe not so much in time, because the afterglows could last for a much longer time than there is an actual record of an afterglow, because gamma ray bursts, once they're uh, observed, they go on a list, on a record that you can look up, and you can look at that and say, oh, this one has this much prompt and this much afterglow, but the afterglow part could be maybe taken with a grain of salt, because pretty much they could have just not done the afterglow in whatever frequency of light. Okay, but maybe you should still keep it as an option for your neutrino search. Okay, so those types of things are implicated. So now, before going into the gamma ray burst theory details, which is in my thesis here, which gives you the what you call which gives you the um, predictions for these different particles. Let me show you a simple diagram that can explain what we're talking about. Okay. Thank you everybody for joining, by the way. And what can you tell us about CERN and antimatter? Hi, my music X. Oh my goodness. Hello, Isabella. Oh, quite a. Can we get 40 likes? Oh, okay. Give me one moment. The the chat is a little crazy, but I am glad everybody's here. Thank you so much for joining and supporting. Um, as always. So, next what we'll do is look at this diagram. Okay? Um, please do subscribe if you're seeing this, okay? Thank you. Um, okay. Thank you, Cosmic Web. Thank you, Cosmic. Thank you, Ben. How are you doing? I see you are busy. Oh gosh. It's 3. Yeah. Okay. So now, real quick before bed, because I realize this is quite an interesting topic. So we might have to pick this up tomorrow. And I always get excited talking about gamma ray bursts. But let me show you a little cartoon I made, which goes over these processes, and we will pick up from there. Okay, next time. So let me turn the camera here. So do you see this? This is basically the collisions that can take place in a gamma ray burst. And we don't know whether this right-hand side of steps actually happen or not. This needs to be confirmed. So see how that there's a red arrow here because we're not entirely sure. This is predicted and it's theorized, but we're not entirely sure if this happens or not. But this does happen. So from these collisions, we basically, this is um, pretty much the steps a flow chart that shows what happens inside a gamma ray burst theoretically, and also we know that there are uh, collisions happening. There is relativistic expansion happening, which leads to certain collisions, and gamma ray bursts are nature's particle accelerators. So in those collisions, you can get accelerated electrons like this left side. And because you have accelerated electrons, you end up getting synchrotron and inverse Compton um, processes happening. And that is where you get the gamma rays from. Okay. So from these, basically from here to here to here. But then if you also had accelerated protons, so this is the hadronic acceleration that I was talking about, then you would have the intermediate uh, particles like the pions and whatnot, which then would decay to give you high energy and ultra high energy neutrinos. So this is what I was talking about, and we will get into some more details of this next time. But hopefully that helps. The one side of it is the leptonic acceleration, and we know that that happens. And the other side of it is the hadronic acceleration, which we don't know if that happens. And we would find out if we saw neutrinos. So neutrinos from a gamma ray burst would confirm that right-hand side, which is really, unknown at this point. And we will get into some of the details of this, like the pions and all that stuff. We will get into that next time. So, because it's a little bit detailed, but I think you will enjoy it because it's it flows really nicely, actually, the logic and the understanding of it. New Jersey, Boston. Yeah, so I think I'm gonna rename it. So I call this Fun and Games. I will say gamma ray bursts. So guys, please come back next time. Please do subscribe and oh my God, my keyboard or my title is getting all messed up. Please do subscribe and watch out for when we are live next because I'd love for us to continue this discussion and speak more about good class and the name Evil Twin. Good night. Hi, Jeremy. Is she real? OMG. I mean, why wouldn't I be real? Uh, you should see my other videos and shorts. How is she so smart? Oh, well, I did go to school for this, long time. And also I worked in this field. So, anyways, please keep coming back to the lives. We talk about these topics pretty much every live, and it had been a while since I talked about gamma ray bursts, but we pretty much often talk about relativity, general relativity, cosmology, um, astrophysics, and these topics. Okay. You blasted off neutrinos and space and stars for like an hour. Yes. Yep. Uh, these topics get a lot easier when that's your bread and butter, you know? So it's not a big deal. It's really not a big deal. This thesis, this thesis is quite old at this point, so I've had some time to get used to it. Yes. Thank you. Thank you, thank you, thank you for the kind comments. Um, so I'm looking forward to talking about the theories of gamma ray bursts that predict the neutrinos because we didn't really cover the details of exactly what that is today. We mentioned it briefly, but I did put in the chat the Waxman paper and I have all of the other papers listed in my thesis in the under the citations, under the references. So you can find all the other papers. So if you want to double check any of this, um, you can. And next time we will go into the more details of exactly how you get neutrinos from the hadronic acceleration and what the intermediate particles are and whatnot. Okay, can we get 30 likes? I feel like we did not get too much engagement today. Maybe people didn't catch us. But hello, ice cream machine. The cats are upstairs because it's a little cold down here. Yes, you should definitely share your kitten pictures. Looking forward to it. I know you had newborn kitty cats. I always learn something new when I tune in. Thank you, Cosmic Web. Thank you so much. Thank you. Good content. Thank you so much. Thank you, thank you. So, we do try to learn something. I do try to cover something new every time. I believe gamma ray bursts is a topic that I actually have covered before. So you should check out, if you enjoy these topics, you should check out my other videos and previous live stream episodes that are all under the live tab of the channel, as well as, I have the video tab, which I'll add more content to, as well as shorts. I hope that you tune into those. To learn more. And we will continue with the gamma ray burst discussions next time because I think actually I enjoyed a lot sharing with you about that this time. I kind of forgot about that topic, but I spent a lot of time working on it. So I can definitely go on and on about it. But I want to break up the sections so that it's a little bit easier to follow. So we can pick up next time with that. It'll be nice. But of course, I wanted to also mention that Waxman and Balkal's papers have all the details for the theory predictions. Okay. All right, Ben. We're gonna name this gamma ray bursts and fun and games. Do you have community? I do have community, and you can share your pictures there. I know some other people do. On my channel, under the community tab, I believe you can go and post whatever you like. So hopefully you're able to see that. I know some other people have sent their photos and posted. Yes, we can collaborate. My hair was weird today. Whatever. Okay, so now with that, Oh, thank you. You should post your telescope pictures on the community tab. Shalom, peace, thank you. Fun and games. Okay, gamma ray bursts, fun and games. Let's catch up. That's gonna be the title. I picked a picture. Oh God. Cosmic web. How are you doing? Thank you, ice cream machine. Come back to the lives. There are lives that are a lot longer. Some people turn them on to sleep. So if you enjoy this content, there's a lot more on the channel. What's the speed of light? Is that a quiz question? Somebody answer it. In what units do you want it? You have to specify. I'm writing several short stories. Oh, wow. Well, please do enjoy, everybody. I hope to see you in the comments of my other videos and shorts and everything else. Please, I appreciate your support very much here on the lives, as well as on the other videos and shorts that you see on my channel. Please do send some love to those as well if you see it, okay? That really helps me out on the channel. It's been a little bit slow, and I think it's suffering a little bit from not having enough engagement um, and whatnot, but that's okay. I'm just happy to see you all here. Okay, I hope to see you next time. Please subscribe and hope you catch us when we're live next. Okay? Hi, Jeremy. It's a little sad, but it's okay. I have been so busy. I feel like I didn't do as many lives lately, and that kind of maybe made my channel suffer. So appreciate your help. Thank you guys so much. Have a good night. Now for the kisses. Are you ready? Mwah, 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 mwah. Good night and love to all. If you see this, please do leave us a comment, like, share, subscribe. Love you, love you, love you. Bye bye. Mwah, 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 mwah. Okay, bye bye. Oh, now I'm going to say goodnight. Good night and sleep tight. Mwah, 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 mwah. You need your energy for the next time that we go live, okay? So please get some sleep in the meantime. Mwah.